Hi, my name is Lena König, and I'm a microbiologist in Silvia Bulgarese's group at the University of Vienna in the Department of Functional and Evolutionary Ecology. I'm also a founding member of Green Labs Austria, a nonprofit organization that wants to inspire a sustainable research culture. And this is a talk about plastics from a global perspective. I gave this talk in our weekly seminar series in fall 2020. This lecture is divided into 4 parts. First, I will talk about plastic production and plastic waste, then about carbon emissions that arise from plastic production, and finally, I'll talk about the pollution of the environment by plastics. You find the references that I used throughout the presentation below the figures. And if you have questions or suggestions, please let me know. And here we go. The talk is entitled The Plastic Wave and How to Maybe Break It. As an intro to the topic of plastic production, you're going to hear a short, iconic scene from the 1967 movie, The Graduate. And in this scene, the importance of plastics at that time becomes clear when the possibility of the future is reduced to a single word, plastics. It was the time when plastics production just started at an industrial scale and people did not yet have environmental concerns. Listen.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Exactly how do you mean?
There's a great future in plastics. Think about it. Will you think about it?
Yes, I will.
Enough said. That's a deal.
Now, this graph shows the amount of plastics produced globally from fossil hydrocarbons, that is, natural gas and crude oil, between 1950 and 2015. And before that, before 1950, plastics did not really exist. The global production increased from 2 million metric tons in 1950 to 380 million metric tons in 2015. And if you sum this up, 7,800 million tons of plastic have been produced in total up to now. Now, how much is 7,800 million metric tons? I calculated that this amount equals the weight of 126 billion people if we assume that the average weight of a person is 62 kilograms. And 126 billion people is 16 times more than the population of today, which is 7.8, by the way. Now, half of these 7,800 million tons were produced in just the past 13 years. And in this graph, bio-based and biodegradable plastics are excluded because so far their production is negligible. Only 4 million tons have been produced globally so far. And you can also see here that this graph only shows the numbers for plastic resins and synthetic fibers. Synthetic fibers are, for example, polyester and nylon. And it doesn't include the additives. What are additives? Additives are added to enhance the properties of plastics. So, for example, additives are plasticizers. They're added to make the material softer and more flexible. Also, flame retardants are additives, for example. And these additives can be up to 50% of a plastic product. So, including additives, 8,300 million metric tons have been produced since 1950. And what is that plastic used for? The answer is that it is used mostly for packaging by far, as visualized in this graph. So this graph shows the share of total plastic resin production according to plastic type, shown here in different colors, and industrial sector, listed on the left, and covering the period 2002 to 2014. And the plastic types marked here with an asterisk indicate the largest groups of non-fiber plastics, which are polyethylene, also called PE, polypropylene, PP, and polyvinyl chloride, which is also known as PVC. So about 44% of plastics are used for packaging, and packaging is predominantly composed of polyethylene, PE, and PE comprises both so-called low-density polyethylene, shown here in orange, and high-density polyethylene, shown here in dark green. The thin and soft packaging you probably know in food packaging is most likely, most of the cases, low-density PE, and the harder type you know from food packaging is in many cases high-density PE. But it could also be PET, which is shown here in purple. You know it from bottled drinks, for example, or polypropylene PP, shown here in light green. Building and construction uses the second largest amount of plastics, about 19%, and importantly uses 70% of all PVC, shown here in red. PVC is often used for pipes and furniture and electric cables. And one of the problems with PVC is that it is hard to recycle, and especially the soft PVC contains a lot of additives, some of which are considered carcinogenic. Of note, not shown here, is the textile industry, which uses fiber plastics. So not resin plastics, but fiber plastics, which is, as I said before, for example, nylon. The produced plastics do have different applications, but what is the long-term fate of plastics? This graph I'm showing here visualizes the global production, the use and fate of all plastics ever made as of 2015. The study factors in estimated product lifetimes to account for how long products are used before they are discarded. For example, most packaging has a lifetime of maybe a year, whereas products for building and construction have a much longer lifetime. They are in use for decades. It is estimated that 2,500 million tons are currently in use. That is about 30% of all plastics ever made. As of 2015, 5,800 million tons of plastic waste have been produced. There are three fates for plastic waste. First, it can be recycled or reprocessed into a secondary material, indicated here by the dark blue arrow, but recycling delays rather than avoids final disposal. It only reduces future plastic waste if it displaces primary plastic production. And second, it can be thermally destructed, mostly by incineration, with or without energy recovery, depicted here as a gray arrow. And third, plastics are discarded, meaning it is contained in landfills or it is uncontained in open dumps in the environment. Discarded plastics comprise the largest group, meaning that 55% of produced plastics ended up discarded. As a side note, 700 million tons of all plastic waste are synthetic fibers. The problem with discarded waste is it doesn't biodegrade in any meaningful way, which means it remains in the environment and only breaks down into small fragments called microplastics. Now, if we don't change our plastic waste production behavior, we will produce about 26,000 million tons of plastic waste by 2050, shown here by the black line. In this graph, the solid lines show historical data from 1950 to 2015, while the dashed lines show projections of historical trends until 2050, assuming consistent use patterns. A large part of the plastic waste, that is 12,000 million tons, will have accumulated in the form of plastic disposed in landfills, that is the red line. And this amount is 2.5-fold more plastic waste than in 2015. Again, this is an enormous mass. It is as much as 9 million giant sequoia trees. It is also interesting to see how the wealth of a country affects the production of waste per person. This graph shows the plastic waste per person and day around the world on the y-axis, plotted against the GDP, the x-axis, in 2010. The size of the circles refers to the population size. In general, low-income countries produce less plastic waste. For example, several African and East Asian countries. However, in these countries, the plastic waste is often mismanaged, so that even though they produce less, the impact for the environment is relatively large. On the other hand, there are high-income countries such as Sweden that produce relatively little plastic waste. That means even 10 years ago, it was possible to manage plastic waste relatively well. In this study that I'm showing you here, there weren't any data available for Austria, and as I only found data for 2018, I added these data to the graph shown here in light blue. So, Austrian people in 2018 produced about as much plastic waste as other European countries, for example Iceland and Portugal, in 2010. So far, I have talked about global plastic production and waste. And next, I want you to know about the carbon emissions that go along with the plastic industry. Conventional plastics, that is fossil fuel-based plastics, created 1.8 billion tons of CO2 equivalents in 2015 over their entire life cycle. And bio-based plastics are not considered here because of the small market share. The inner circle of this figure shows the fractions of emissions per life stage. You can see that the production stage generated the big part of emissions, that is 61%, shown here by the blue part, followed by the conversion stage in orange and making up 30%. The plastic production includes extraction and transport of oil and gas, as well as making the plastic monomers and polymers. In the conversion stage, products are made out of plastic polymers. The outer ring shows the share of emissions by plastic type. Interestingly, as you can see, PP&A plastics, meaning plastic fibers used in textile industry, and it stands for polyester, polyamide, and acrylic fibers, they account for the highest emissions in both the production and conversion stages. Surprisingly, the so-called end-of-life stage, so the final fate of plastics, in green, accounts for only 9% of emissions. Not surprisingly, however, incineration was the dominant source of emissions at this stage. Also, the process of recycling itself has a carbon footprint, although it's smaller than the other processes. If recycling is included in the emission calculations, the global greenhouse gas emissions go down a bit to 1.7 billion tons of CO2 equivalents, because a part of virgin plastics production is displaced by recyclates. But how much greenhouse gas emissions are we talking about? I told you before that 1.8 billion tons of CO2 equivalents were produced in the year 2015 from plastic production, conversion, and end-of-life treatment. Let's put that into perspective. Assuming that the global average plastics production per capita in 2015 was 55 kilograms, a bit less in Africa and a bit more in Europe and North America. And assuming that for 1 ton of plastic produced, about 5 tons of CO2 equivalents are emitted, one person had an average plastic emission of about 277 kilograms of CO2 equivalents in 2015. 277 kilograms of CO2 equivalents is approximately the same emission produced during a flight from Vienna to London per passenger. 277 kilograms of CO2 equivalents also equals the emission produced from a beef burger that is eaten once in 2 weeks over a year. Considering that many of us eat meat more than just once in 2 weeks, the greenhouse gas emissions from the meat industry are much larger than the plastic emissions. But the emissions associated with plastics are still substantial. In 2015, the global greenhouse gas emissions were 47 billion tons of CO2 equivalents. The whole plastic life cycle emissions contributed 3.8% of emissions, while transportation accounted for 16% and the whole food supply chain 26%. But plastic emissions are projected to grow. This figure shows that if plastic production is to grow as before, that is 4% average annual growth rate, and if the energy is a mix of fossil fuel-based and renewable energy sources, as it is now, and the end-of-life fate of plastic is a mix of landfills, incineration, and recycling, then plastic emissions from fossil fuel-based plastics will grow to 6.5 billion tons of CO2 equivalents by 2050. This projection is depicted by the blue line. Shaded areas show the projection depending on different end-of-life fates. The upper area shows the projection if all waste is incinerated, and the lower areas show the projection if all waste were to be recycled. So, if all fossil fuel-based plastics were to be incinerated, the emission would be 8 billion tons. And if it all were to be recycled, the emissions would drop to 4.9 billion tons by 2050. How do projections look like for bio-based plastics? So if fossil fuel-based plastics would be gradually replaced with bioplastics by 2050. Bio-based plastics are made from renewable biological sources such as corn and sugarcane, here shown in yellow and green. Projections for bio-based plastics show that emissions would be lower by 2050. The reason is that the emissions from the production of plastics from these renewable resources are lower. Interestingly, the projections also indicate that complete recycling of fossil fuel-based plastics could be as beneficial in terms of emissions as using bioplastics if the bioplastics had a mixed end-of-life fate. You can see that in the right graph, which depicts the projected emissions in 2050 depending on the different end-of-life options. I also want to point out here that there are different types of bioplastics. They all have in common that they are made from renewable resources, but they can be processed to produce polyethylene, PE, which is chemically the same as PE produced from fossil hydrocarbons, and therefore is hardly biodegradable. Or they can be processed to produce, for example, polylactic acid, which has the distinct advantage of degrading to non-toxic products. Now let's take a look at the projected emissions in other scenarios. Assuming that by 2050 we only use renewable energy, shown here in the left panel, emissions would be substantially reduced compared to the first scenario, even if we keep using fossil fuel-based plastics and would incinerate it all. See the blue triangle. However, emissions would still be increased compared to now. If we were to recycle all plastic waste using renewable energy, we could achieve a real reduction, even if we used fossil fuel-based plastics. See the blue square. In the scenario in which simply the plastic production is reduced to 2% growth per year instead 4%, the emissions cannot be lowered below the current level. This is shown in the center panel. The best scenario is the one in which plastic production is reduced and 100% renewable energy is used, depicted in the right panel. Here, the emissions are constant if we only used fossil fuel-based plastics and had a mixed end-of-life fate. If we replaced fossil fuel-based plastics with bioplastics, we could potentially reduce emissions further, especially if those were all recycled. Now, if plastics are not recycled or incinerated, they potentially end up in the environment, so they cause plastic pollution. And as you know, that's a major problem for health and ecosystems, as it is virtually non-degradable. Plastic pollution can be found in oceans and rivers and lakes, in soil and sediments, and even in the atmosphere and in animal biomass. This map gives an overview about global plastic pollution. Purple areas show the concentration of plastics floating in the oceans. Importantly, plastics have been found on the surface of all oceans. Plastics are moved by wind and currents and slowly broken down by their exposure to water and light. Some of the plastics end up offshore in one of the 5 principal gyres. Those are large rotating systems that slowly move the floating debris towards their centers, resulting in large areas of high plastic concentration. Other areas of high concentration can be seen close to river mouths and in marginal seas with low levels of water inflow, like the Mediterranean Sea. The circles show the annual amount of plastics that enter oceans via rivers. Wind and rain carry plastics into rivers, and rivers carry plastics from land to the oceans. It is estimated that 8 million tons of macroplastics and 1.5 million tons of microplastics enter the oceans annually. The brownish areas on land indicate the amount of mismanaged plastic waste per year, so it tells us how much inadequately disposed waste is produced around the world. And therefore, it tells us how likely it is for plastic waste to end up in the environment due to littering, illegal dumping, and poorly designed waste management systems. You can see that mismanaged plastic waste is a problem in highly populated areas, and even more so when this coincides with low income. Plastic pollution has various severe consequences. Ingestion and entanglement are well documented scientifically, and both have been reported for many marine and freshwater animals, but also terrestrial animals. As ingestion and entanglement can lead to death of animals, it can consequently cause the change of assemblages, which may affect biodiversity. A study from 2017 has found evidence that microplastic particles are transferred from soil to chickens through earthworms. This graph from that study shows that the number of microplastic particles increases from soil to chicken, indicating that they accumulate as it goes up the food chain. Plastic pollution also has an effect on microbial life. For example, this study from Gerhard Handel's group in 2018 found that dissolved organic carbon leaching from plastics stimulates microbial activity in the ocean. And one can imagine that plastic particles affect the human microbiome and also soil chemistry. Furthermore, human health is affected in that microparticles and nanoparticles are associated with oxidative stress and inflammation. Plastic additives can get into the food web, causing disruption in our hormonal system. And plastic particles can also be immunotoxic, potentially increasing infectious and non-infectious diseases. It has also been reported that plastic pollution facilitates the dispersal of microbes and that particles can serve as breeding grounds for disease vectors such as mosquitoes. But plastic pollution also has negative impacts on the economy as it damages drainages and wastewater systems and interferes with fishing, tourism, and shipping industries. So far, I have talked about plastic production and waste and also carbon emissions and plastic pollution. I will now turn to this recent, really extensive study entitled Evaluating Scenarios Towards Zero Plastic Pollution, which was published just last year. And in this study, the authors estimate the effectiveness of different measures to reduce plastic pollution. To do so, they modeled stocks and flows of plastic waste through the entire global plastic system. They called it the plastics to ocean model. It is a data-driven, coupled ordinary differential equation model, in case someone was wondering. The model was informed by an expert panel consensus, by historical trends, by interviews with industry experts, and purchased proprietary data from industry databases. Also, plastic masses and flows were modeled for 8 geographic archetypes, which were defined based on income and distance to water. In their model, they include 4 types of materials, that is, rigid monomaterial plastics, flexible monomaterial plastics, multi-material, multi-layer plastics, and microplastics. And the model includes 4 microplastic sources, that is synthetic fibers, tires, plastic pellets, and personal care products. The output was an annual estimation of terrestrial and aquatic pollution from 2016 to 2040, with pollution defined as plastic waste input into the environment. Now, the key aspect of the study is that with this model, the authors estimated pollution for 5 different scenarios. Each of the 5 scenarios was defined by a set of specific but feasible measures. They are called here interventions, which I will show you in the next slide. Here I listed the 5 scenarios and the interventions they entail that were modeled to evaluate plastic pollution. Importantly, the interventions considered were assessed for their feasibility, so they had to be safe in terms of health and food. They had to be affordable and technologically ready and accepted by consumers. The first scenario is the business as usual scenario with no interventions. The second scenario is the collect and dispose scenario, and this includes increased collection of plastics, reduced post-collection leakage into the environment by building landfills and incinerators with energy recovery, and reduced export and import of plastic waste. The recycling scenario includes the following interventions: redesign of materials, measures to improve recycling, also increased collection, increased scale of plastic sorting and mechanical recycling, increased plastics to plastics conversion. The reduction and substitution scenario is about reducing plastic use and substituting with alternative materials, such as paper, for example. and consequently also, like in the collect and dispose scenario, reducing export and import of plastic waste. In the system change scenario, all of the interventions mentioned above are implemented. And scenarios 2 to 5 additionally include the full implementation of government policies and industry commitments that were developed between 2016 and 2019, for example, the EU Single-Use Plastics Directive. Now let's take a look how much the different scenarios affect plastic pollution. The panel here shows the combined annual plastic pollution rates, that is aquatic and terrestrial pollution rates. If we consider the business as usual scenario to generate 100% plastic pollution, the red line, then the plastic pollution was reduced by 57% and 59% in the collect and dispose and reduction substitution scenario respectively. Those are the blue and yellow lines. And a bit less reduced, that is 45% in the recycling scenario, the green line, in 2040. This means that if we implemented the collect and dispose or the reduction and substitution scenario, plastic pollution in 2040 would be a bit reduced compared to now, but it would still be a bit higher than now if we implemented the recycling scenario. Interestingly, if we just implemented all government policies, that's the black dot in this figure, there would only be a slight reduction of plastic pollution compared to the business as usual scenario in 2040. So, implementing what has been proposed so far by the governments and the industry is not enough to really reduce plastic pollution. However, in the system change scenario, the purple line, and remember in this scenario all interventions are implemented, there is a plastic pollution reduction by 78% predicted compared to the business as usual in 2040. And compared to 2016, a reduction by 40%. In other words, with current knowledge and technology, 78% of the plastic pollution problem could be solved by 2040. Also, relative costs for each scenario were calculated in the study. Costs were reduced by 18% under the system change scenario compared to the business as usual scenario, and were highest under the collect and dispose scenario. In the system change scenario, increased waste management costs were offset by cost savings from reduced plastic production and revenues from sales of recyclates. So the system change scenario is cheaper than the business as usual scenario and reduces plastic pollution, both terrestrial and aquatic, substantially. However, it requires immediate, extensive, and global interventions as depicted in this infographic. I have listed all of the necessary 8 interventions before, but I will just summarize them again here because I find them so important. All around the world, we have to first reduce plastic consumption so that 1/3 of plastic is avoided. Second, substitute with materials from renewable resources to avoid 1/6 of plastic waste. Third, increase the share of recyclable plastic products to 54%. Fourth, scale up plastic collection, especially in middle and low income countries. Fifth, the recycling capacity has to be doubled by 2040. Sixth, plastic to plastic conversion has to be developed so that the plastic that exists can be reused as plastic. Seventh, plastic waste has to be disposed of safely. In this scenario, only 23% of plastics cannot be recycled. And eighth, export of waste to countries with poor waste management has to be reduced by 90%. Even in the system change scenario, however, a substantial amount of plastic waste remains unmanaged, which means it is not collected and sorted, recycled, or safely disposed. Even if we had implemented all interventions in 2020, we would add 250 million tons of plastic pollution to aquatic systems and 460 million tons to terrestrial systems by 2040. This is approximately 1 and 2 times the total annual plastic production in 2016, respectively. If we delay the implementation by 5 years, we add another 300 million tons of plastic pollution. Now, what are the most prevalent plastic types polluting the environment? This graph shows the proportion of plastic pollution entering global aquatic on the left and terrestrial systems on the right by plastic type between 2016 and 2040. You can see that in both systems, the flexible monomaterial plastics, the blue lines, represent the largest group of plastics entering the environment throughout the time period. And the proportion of microplastics, the purple lines, would substantially increase. That is because the collection of microplastics is expensive. And apparently 93% of microplastics is derived from tire particles. At the end, I want to briefly touch upon subjects I haven't yet covered in this presentation. Bad news first. In 2020, a study came out showing that even the most isolated areas in the United States that are national parks and national wilderness areas accumulate microplastic particles after they are transported there by wind and rain. And the authors estimated that more than 1,000 metric tons per year are deposited there. And they also found that most of the plastic particles were derived from synthetic fibers, so the type of plastic that is used in the textile industry. Plastic recycling has been in the media a lot lately. For one, plastic recycling has been impacted by the pandemic, in that the pandemic caused oil prices to drop, which made it cheaper to make plastics out of fossil fuels than to use recyclates. And second, plastic recycling is seen as a fraud by some, as it doesn't solve the problem that too much plastics are produced, and thus tricks us into believing it is the answer to plastic pollution. Also, most types of plastics are difficult to recycle because it is expensive and they contain toxic components. However, most experts agree, and also the study I just presented to you shows that plastic recycling, if done right, is absolutely a necessary action to bring down plastic pollution. And last on this list of bad news is that there is a push from the powerful oil companies to sell oil to the plastic industry in order to counteract their losses in the transportation industry. On the positive side, there's research going on aiming at finding microbes that can degrade plastics. And in 2016, a Japanese team of researchers isolated a bacterium that can grow on PET plastic. This is what most plastic bottles are made of. And they also identified the enzymes responsible for degradation. And in 2020, these enzymes were linked to create a super enzyme that can degrade PET considerably faster than before. So, in addition to many other efforts, these engineered enzymes could possibly contribute to reducing plastic pollution. Furthermore, until recently, Europe shipped large parts of its waste to China and other countries, therefore kind of diverting and blending out the waste problem. And then, at the beginning of 2018, China banned the import of solid waste, including plastics, which forced the EU to really face the mounting waste. In fact, shortly after, the EU launched the Circular Economy Action Plan as part of the European Green Deal. And this plan introduces measures for a circular economy in general, and for example, measures to keep resources such as plastics in the EU economy for as long as possible. And this also entails increasing recycling of plastics to 50% by 2025. I would say that collectively, the EU initiatives are pointing in the right direction. Finally, I hope you found this lecture informative, and thank you so much for listening.